Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication system. Previously what we have seen is we have seen the impact of delay spread on wireless communication. Now what we are going to see in this module is another key parameter of the wireless channel, which is termed as the coherence bandwidth. So what we are going to see in this module is for a wireless channel, we are going to see another important parameter of the wireless channel, which is termed as the coherence bandwidth of the wireless channel. This is termed as the coherence bandwidth of the wireless channel. Now naturally we are saying bandwidth, the bandwidth relates to frequency. Therefore we have to look at this wireless channel in the frequency domain, right. So far what we have looked is, we have looked at a time domain characterization of the channel. So we have said, so the channel in the time domain, what we have said is, we have a signal that is transmitted, and this is our wireless channel model. So we have a signal that is transmitted. So xt is the transmitted signal, yt is the received signal, ht is the, so this is the channel response or the impulse response of the channel. Therefore now we know at the output from theory of LTI systems, we know that the output yt equals, you can easily recall, yt equals xt convolved with the response ht, where the star operator, this is an important operator in LTI systems, this is termed as the convolution. So the received signal yt is the received signal, ht is the response of the channel, and xt is the transmitted signal. We can see yt equals xt convolved with ht. Now therefore in the time domain, if it is a convolution, we know that in the frequency domain, therefore I can write yf equals the product of xf times hf, where yf is frequency response of Fourier transform of the received signal, h1 is the channel frequency response, and xf is the frequency response of input signal, or basically the Fourier transform of the input signal that describes the frequency components of the input signal in the frequency domain. So I have yf is equal to xf times hf in the frequency domain, that is convolution in the time domain is a multiplication of the frequency responses in the frequency domain. And now we can see what happens in this scenario. Now consider this scenario, we can consider two scenarios. The first scenario is where, let us say, my transmitted signal xf has a certain frequency response, this is xf, and let us say my channel has a certain response HF. So, the channel has a certain response, that is HF, and this is, you can see this is the bandwidth of the signal, that is Bs, which is less than the bandwidth of the channel, that is Bc, that is the flat portion of the bandwidth of the channel, that is Bc. And now for this scenario you can see that since the bandwidth of the signal is less than the bandwidth of the channel, when you multiply the signal with the bandwidth of the channel, you can see that there is no distortion, that is when you have Xf into Hf equals Yf, because Bs, that is Bs is less than the Bc, there is no what you can see is the following thing, that is what we are saying is basically there is a signal which has a bandwidth Bs and there is a channel which has a bandwidth Bc, that it is flat over the bandwidth Bc. Now, at the output what you are saying? You are saying basically the Xf multiplied with Hf, which is the response of the channel. Now, if Bs is less than Bc, that is Bs basically is within the flat portion of the channel, that is the bandwidth Bc of the channel, then when you multiply Xf with Hf, the resulting Yf is not distorted, because the signal bandwidth Bs is less than the bandwidth Bc of the channel. This is known as, this quantity Bc of the channel is known as the coherence bandwidth of the channel. This quantity Bc is an important quantity. This is known as the coherence. This is known as the coherence bandwidth of the channel, and this scenario when Bs is less than Bc, this is known as a flat fading channel. Why is it a flat fading channel? Because the signal bandwidth is within the flat portion of the channel bandwidth. So, such a scenario is known as a flat fading channel scenario. There is no distortion. This quantity Bc, or the bandwidth of the flat portion of the channel, is known as the coherence bandwidth, and therefore, when the signal bandwidth Bs is less than the coherence bandwidth of the system, there is no distortion in the frequency domain. Now, let us look at the other scenario when Bs is greater than Bc. Now, when Bs is greater than, let us say this is my signal with bandwidth Bs, and this is greater than my channel bandwidth. Let us say my channel has a smaller bandwidth, this is my Bc. Now, clearly you can see this Bs, bandwidth of the signal, is larger than the bandwidth of the channel. So, this is my signal bandwidth Xf, this is my channel bandwidth Hf. Signal bandwidth is less than the channel bandwidth. Therefore, when I multiply the signal by, when I multiply this signal by the channel, there is going to be a distortion, and therefore, what you will get is, you will not get the original signal, but Yf is equal to Xf times Hf is basically there is distortion. You can clearly see there is distortion. Why is there distortion? Because the signal bandwidth Bc is greater than signal bandwidth Bs is greater than Bc, which is the coherence bandwidth of the channel. So, when you have coherence signal bandwidth is greater than the coherence bandwidth, when the signal bandwidth Bs is greater than the coherence bandwidth, that is greater than the flat portion of the channel bandwidth, which is Bc, then when you multiply the signal Fourier transform with the channel Fourier transform, what you get at the receiver is basically a distorted version of the frequency response of the signal, and this is arising because the signal bandwidth is greater than the coherence bandwidth of the channel, that is Bs is greater than Bc, and this is termed as frequency selective fading. This is termed as, and this is termed as frequency and this is termed as frequency selective fading. So, we have two scenarios here. One is, first is we have defined the coherence bandwidth, and we have said this is basically equal to the flat portion. This is basically equal to the flat portion of the channel bandwidth. Further, what we have said is, if Bs is less than Bc, this implies flat fading with no distortion. On the other hand, if Bs is greater than, if Bs is greater than Bc, this implies frequency selective fading and there is going to be, and there is also going to be distortion. If Bs is signal bandwidth is less than coherence bandwidth, there is no distortion, it is a flat fading channel. If signal bandwidth Bs is greater than the coherence bandwidth, then there is going to be frequency selective fading, then there is going to be distortion, right. And now therefore, let us look at how to characterize this coherence bandwidth. Observe that the channel model is given as h of t is summation I equal to 0 to L minus 1 ai delta t minus tau I. This is basically the channel impulse response, multipath impulse response of the channel. Now, we also know that each delta t minus tau I, the Fourier transform of this is basically integral minus infinity to infinity delta t minus tau I e to the power of minus j 2 pi f tau I f ft dt, which is equal to e to the power of minus j 2 pi f tau I. So, each delta t minus tau I has a Fourier transform which is e to the power of minus j 2 pi f tau I. Therefore, if I look at summation I equal to 0 to L minus 1 ai delta t minus tau I, it has a Fourier transform which is given as I equal to 0 to L minus 1 ai e to the power of minus j 2 pi f t I. So, what I can see here is that delta t minus tau I has a frequency response which is, or Fourier transform which is e to the power of minus j 2 pi f tau I. Therefore, summation I equal to 0 to L minus 1 ai y has a Fourier transform which is summation I equal to 0 to L minus 1 ai e to the power of minus j 2 pi f tau I. So, this is the Fourier transform. What is this? This quantity, if I write it here, let me write it here clearly. Summation I equal to 0 to L minus 1 ai e to the power of minus j 2 pi f tau I. What is this? This is the Fourier transform of h of t, which is the Fourier transform of the, or Fourier transform of the channel response. This is basically our h of f. This is the Fourier transform of the h of t, or Fourier transform of the multipath this is the Fourier transform of the multipath channel response. Now let us look at a typical component. Let us look at e to the power of minus j. Let us look at this component e to the power of minus j 2 pi f tau I. Now let us consider two cases. At f equal to 0, the phase equals 2 pi f tau I. If f equal to 0, this is equal to 0. At f equals 1 by 2 tau I, what is the phase? The phase is equal to 2 pi 1 by 2 tau I times tau I, which is equal to pi. Alright. So let us look at this component e to the power of minus j 2 pi f tau I. At f equal to 0, the phase is 0, right. At f equal to 1 over 2 tau I, the phase is pi. So the phase has changed significantly from 0 to 1 over tau I, which means the frequency response has changed significantly. That is, the frequency response at 0, which is flat, has changed significantly at f equal to 1 by tau I. Therefore, what we can say is phase has changed significantly or in other words frequency response has changed significantly at f equal to 1 at f is equal to 1 by 2 tau I, implies the bandwidth is twice this frequency, which is twice 1 by 2 tau I, which is equal to 1 by tau I. So for each of these components, for this is for the ith path, remember for the ith path, the frequency response has changed significantly from f equal to 0 to f equal to 1 over 2 tau I, which means the bandwidth associated with this is twice into 1 over 2 tau I, which is 1 over tau I. So the bandwidth roughly associated with each component is 1 over tau I. Now if you look at the average of these, now what are these tau I's? The tau I's are nothing but basically the various delays. So now if we look at the average, therefore the average spread or the average bandwidth, one can think of it as 1 over sigma tau, where sigma tau is the delay spread. Therefore in general approximately the bandwidth of channel is equal to, that is, if I look at the bandwidth is equal to 1 over sigma tau, which is equal to the coherence bandwidth. The bandwidth is nothing but the coherence bandwidth. This is equal to 1 over sigma tau. So we have this relation, we have this beautiful relation which we have derived intuitively. This is 1 over sigma tau, where BC is the coherence bandwidth and sigma tau, remember sigma tau is our delay spread, and therefore what we are saying is a coherence bandwidth is the inverse of the delay spread. That is, the larger the coherence bandwidth, the smaller the delay spread. That is, the smaller the delay spread, larger the coherence bandwidth. larger the delay spread, smaller the coherence bandwidth. As the delay spread increases, the coherence bandwidth decreases. Okay, and further we have seen that sigma tau is equal to 2 microsecond in the previous module. Therefore, the coherence bandwidth of the typical outdoor channel is 1 over sigma tau equals 1 over 2 microsecond, which is equal to, so this is coherence bandwidth, typical coherence bandwidth is 500 . What we are saying is that the typical coherence bandwidth is 500 kilohertz. That is, because the typical delay spread is 2 microsecond, typical coherence bandwidth is 1 over the delay spread, which is 1 over 2 microseconds, which is 500 kilohertz. Now let us look at something interesting. Let us look at something interesting. We said frequency selective distortion occurs if signal bandwidth is larger than the coherence bandwidth. That is, we said frequency selective distortion occurs if Bs is greater than Bc, but remember Bs is equal to 1 over T, where T is the symbol time. That signal bandwidth is simply 1 over the symbol time, and also coherence bandwidth is 1 over the delay spread, right. So, we are saying frequency selective distortion occurs if Bs is greater than Bc, but Bs is 1 over T, Bc is 1 over sigma tau. Therefore, frequency selective distortion occurs if 1 over T is greater than 1 over sigma tau, which implies, very surprisingly, sigma tau is greater than T. And have we seen this before? We have seen this in the previous module, that is, the delay spread is greater than the symbol time, and this is precisely intersymbol interference. This is precisely the condition for intersymbol interference, right. So, what we are saying is something very interesting, that is, if Bs is greater than Bc, that is, signal bandwidth is greater than the coherence bandwidth, that implies that the delay spread is greater than the symbol time, which is the same thing as intersymbol interference. So, what we are saying is frequency selective distortion and intersymbol interference are one and the same. While frequency selective distortion is in the frequency domain, the corresponding equivalent analog in the time domain is intersymbol interference. And therefore, parallelly for frequency flat fading, it means no intersymbol interference in the time domain, right. So, similarly, for frequency flat fading, it means there is not going to be any intersymbol interface. Therefore, we have a very beautiful interpretation of what is going on in the wireless channel, and that can be summarized as follows. I want to write the summary. The summary is, if Bs is greater than Bc, this implies that sigma tau is greater than T, which implies frequency selective fading, which also implies ISI, which is intersymbol interference. On the other hand, if Bs is less than Bc, that implies sigma tau is less than tau, the delay spread is less than T, which implies basically frequency flat fading and which also implies no ISI. So, this is a very important property of a wireless channel, which is if Bs is greater than Bc, automatically it is frequency selective fading and there is intersymbol interference in the time domain. If Bs signal bandwidth is less than the coherence bandwidth, it is frequency flat fading in the frequency domain and there is no intersymbol interference in the time domain, that is there is no distortion. And therefore, this is a key aspect. What we have done in this module is we have defined this new parameter, which is the coherence bandwidth, to characterize the wireless channel, and along with that what we have done is we have seen the impact of how these parameters relate, the coherence bandwidth, the delay spread and the impact, the interplay between these various parameters in terms of the intersymbol interference, frequency selectivity and also distortion at the receiver. So, this is a very important sort of module which summarizes the various things or the various effects that are occurring in the wireless channel, and we will look at the other effects, the other important aspects of the wireless channel in the subsequent modules. Thank you very much.